So it's a pleasure to be here, or at least virtually. It's an advantage of having Zoom in these days that we can actually still get together a little bit. And I'm speaking today about the Gödel and the lengths of proofs. It's a second here. So this is really somewhat of a historical talk. So I should start off by saying, though, that proof complexity and proof length are very actively studied nowadays. From my point of view, especially due to their connections to computational complexity and even to automated theorem proving. It's a very active area now, but there's also a lot of interest in proof lengths and studying the lengths of proofs in stronger systems such as first order logics and higher order logics. And as I said, this is going to be a historical talk primarily. I want to talk about the things that Gödel did with the lengths of proofs, and then also some of my own contributions a bit more than 25 years ago, I guess. Gödel was actually the first one to study the lengths of proofs, and he did this primarily in a very short paper in 1936 that was done without even giving any proofs of the assertions he made. And I want to talk about that. That's the second bullet point on the list. I want to talk about also a comment on the lengths of proofs made by Gödel in a letter to von Neumann 20 years after that, very closely related to the P versus NP question. It was one of the first written records of people explicitly studying the question of whether P equals NP. And the first point I'm going to talk about, though, is something Gödel didn't discuss, but he could have, which is partial consistency statements or finitistic consistency statements for symbol length. And I'll get to all of these definitions in a minute. And now, as I was preparing this first slide and I was writing the phrase, Gödel was the first one to study the lengths of proofs, I was reminded of this quote by Frege, which I wrote here in very small font at the bottom of the screen, so you don't necessarily need to feel like you read this, but this is from his Grundgesetze in 1893, thus certainly preceding Gödel. His starts off with, the length of a proof ought not to be measured by the yard. In other words, you shouldn't just take the sheer length of a proof as the most important measure. And he goes on to say that it's important to fill in the details and show every step of the proof. In other words, it's important to give a proof in the modern sense of a proof. So although Frege didn't explicitly study lengths of proofs, he did mention them at least at one point. So this, as far as I know, is the first mention of the length of proof in logic literature. If anyone has an earlier reference to this, I'd be delighted to hear it, of course. Let's see. Also, let me say, I'm happy to have questions and interruptions during the talk. Just break in. I probably won't. You can either post in the chat window, I might notice it, or you can just speak out loud and hopefully I'll hear you. So, so please feel free to ask questions as I go along. Okay, so some preliminaries. Just a second here. Okay, so we're going to work mostly in first order theories or higher order theories. And for the most part, theories of arithmetic, at least the first two parts of the talk, either extending primitive recursive arithmetic or more generally this bounded arithmetic theory S12, which is a theory tailored for polynomial time in the first order setting. We just saw some constructions in the previous talk for P time, and this is a different theory of approaching P time based more in the style of PA. You don't need to know any details of S12, though. I'll remind you of anything important when we get to it. And the results I'm talking about work in the usual Hilbert style formalizations, and most of them work also in the sequent calculus, although there's some open questions about that. So our notation here, I think people can see my mouse if I come on the screen. I use a T turnstile phi with superscript n to mean that the theory T has a proof of the formula phi of symbol length less than or equal to n. So symbol length means we write out the proof as a string of symbols and we count the number of symbols occurring in the proof. And that should be less than or equal to n. And just to be a little careful here, one could be a little picky about what is a symbol. So is a symbol a traditional symbol, or do we count the subscripts on variables as part of the symbols? And the answer here is it doesn't matter too much. All the theorems I'm going to state will work either way. We use subscript n on the next bullet point. Let me see if I can do something here better. T turnstile sub n phi means that T has a proof of phi of step length less than or equal to n. So step length means the number of formulas appearing in the proof. Then we write the consistency statement. This is a finitary or partial consistency statement. Con T of n, it's a first order formula expressing in a natural way that T has no proof of a contradiction of symbol length less than or equal to n. And this is written out formally as, as written here on the screen. There does not exist an X, proofs of T of X, Gödel number of 0 equals 1, and the symbol length of X is less than or equal to n. And I think everyone's familiar with how this is done in the Gödel's incompleteness theorems. And so in the second incompleteness theorem. So I will just say that we're working in theories where this can be done in a natural way. And with a superscript step, con T step n is the same assertion, but for step length instead of symbol length. And these are called partial consistency statements or finitistic consistency statements. To the best of my knowledge, they were probably considered first by Harvey Friedman and Pavel Pudlak in the papers I'll mention on the next slides. But again, if anyone knows more of the history of this than I do, it'd be great to hear it. Okay. So for the first results I want to touch on, we want to look at lower and upper bounds on the length of proofs for partial consistency statements. So we'll let T be one of the usual theories of arithmetic in one of the usual ways of Hilbert-style calculus formulation. We'll let n be an integer, and T will be a closed term denoting an integer or an integer as defined by a delta naught formula. And the theorem here gives lower bounds on the lengths of the proofs of these partial consistency statements. So the first observation is, let's take something like con T of n. I should actually have written this on the slide, but I didn't. So con T of n says there's no proof of a contradiction with less than or equal to n symbols, right? Well, how many proofs are there with less than or equal to n symbols? There's only finitely many of them, right? So you could just go through all possible proofs and all possible strings of length n symbols, I should say, and verify that none of them is a valid proof of 0 equals 1. So T can certainly do this, but this would be an exponentially long proof because there's exponentially many strings of length n. So that gives an upper bound, and we'll see a better upper bound in another couple slides. But the theorem here is that there is an epsilon greater than 0, so that T cannot prove in n to the epsilon symbols the partial consistency statement con T of n. So if you want to prove that there's no proof of a contradiction of less than 1 million symbols, right, you're going to need a proof of, say, at least 1,000 symbols or something like that, right? And I stated that the first bullet point is for a particular integer n. The second one is for just a value as given by a term T. The same theorem holds. It's not the case that T proves in T to the epsilon many symbols con sub T of little t. So one remark here on the first bullet point, and this is written on the bottom of the slide in very small font, is the integer n, we don't use the usual successor notation for the constant denoting the integer n. We use a binary encoding for numerals. So this n underline value here is a term with value n, but it has length order log n. So the length of the statement con T of n is only order log n statements. So we could talk about short proofs of it. As a side remark, Pavel Pudlak improves the n to the epsilon lower bound to a bound of omega n over log squared n. under a suitable formalization of a Hilbert-style system using Rosser's rule C. And Rosser's rule C is just, if you have a statement exists x 5x, it allows you to introduce a constant c such that 5c holds. So in that case, proofs can be made a little more efficient, and in particular, you can get a sharper lower bound. The other comment is that because we can define very large values t with delta naught formulas, the second part, that t doesn't have proofs of length t to the epsilon of con t of t, gives us a nice way of forming short sentences that are true but require very long proofs. Okay, so why am I introducing this in the context of Gödel's and lengths of proofs? Because this uses just a classic Gödel method of self-referentiality, saying we get a phi that says it does not have a short proof, and then we show that in fact phi doesn't have a short proof, and then we use that to show that con t of n doesn't have a short proof. We already saw this kind of argument in Sergei's talk a couple days ago, if you were here on Tuesday. But I'm sorry. Maybe, well, I don't actually, I stated that wrong. His results were for 2 slides on in my talk, I believe, Sergei. Yes, he can correct me if I'm wrong there. I can't hear you.
I'm watching, yes, good, thank you.
Okay, good. Yeah, sorry, I'm getting ahead of myself with that comment. So here's the proof sketch, and this very much follows the usual proof of the Gödel incompleteness theorem. We can diagonalize in the usual way and get a formula phi that says it, or a sentence phi that says it doesn't have a short proof. And furthermore, t proves this fact. So t proves that phi is equivalent to the statement, there does not exist a proof of phi of symbol length less than or equal to n to the delta. And then delta is some small constant, which we'll see in a minute where it has to be. And now I claim that phi is true since t is consistent. I guess I didn't mention earlier that I was only considering consistent theories t, but I am. I'm being a little hand wavy at times, right? I'm also assuming things like t is recursively axiomatized in a nice way and so forth. Okay, but putting that aside, t can prove the statement that not phi implies phi as a proof of n to the delta symbols in t, right? Just by the definition of phi, right? If you look at phi is equivalent to not something or other, so not phi is equivalent to the something or other, right? And furthermore, a little more substantively, t can prove that not phi implies that t has a proof of not phi, and that proof has length n to the delta k for some value k, for some constant k, an integer k. And this is just because phi is a true existential statement. We can formalize, for those of you who know this stuff, we can formalize this appropriately in S12, and there's a nice theorem that says that any true sigma v1 formula has a polynomial size proof in S12. More intuitively, you can think about the fact not phi is an existential statement. And how can you prove an existential statement? Well, if the existential statement is true, you just take the value x that makes the existential statement true, and you just check that x makes that existential statement true. And that's just a bounded formula, and t can prove it. And doing this carefully, the length of the proof is given in terms of some, can be bounded by n to the delta raised to the power k. So we can think of phi as having this parameter n to the delta, and then we can say the proof of these assertions have a polynomial degree k blow up in the size. So at any rate, putting those together, t proves that if not phi holds, then t has short proofs of both phi and not phi. So t proves that if not phi holds, phi has some short proof of a contradiction. And putting that together, then we get t proves, taking the contrapositive, t proves that the consistent con tn implies phi, assuming we chose delta less than 1 over k, basically. And so then we can't have short proofs in t of con t of n, because short proofs of con t of n would then use modus ponens to get a short proof of phi, but phi doesn't have a short proof. Okay, so there we are, that's the proof. So I belabored this a little bit just because it's a very basic, simple result, but it's certainly a proof Gödel could have given had he thought of it, right? But it was something that was only discovered much later. Okay. And then there is an upper bound also. Pudlak showed that in fact, for some constant k, bigger than 1 here, T has polynomial size proofs of con T of n. And this is the result Sergey sketched the proof of 2 days ago. So I will just say very quickly the proof idea, which is to use partial truth definitions for symbols of length of formulas of symbol length less than or equal to n. So formulas of single length less than or equal to n, we can give a partial truth definition that correctly reports on the truth of formulas of that size. And then you can prove that every line of a proof in which all formulas have size at most n is true under that partial truth definition, and 0 equals 1 is not true under that partial truth definition, and hence there could not have been a proof of 0 equals 1. Pudlak actually improves this to this upper bound of n to the k to the O of n, based on bounds on formula complexity that come out of unification results, especially of row heap Parikh, and later related constructions of Kryacek and Pudlak. And interestingly enough, in many circumstances, the theorem also holds for step length. In other words, there are polynomial symbol length proofs of T of the step length consistency of T up to length n. And the same unification techniques can be used to limit the formula, the logical complexity of formulas in a proof of step length n. And once you have a limit on the logical complexity, that doesn't limit the term complexity, but eliminates the number of quantifiers and logical connectives in any formula. Once you have a limit on the number of logical connectives in a formula, you're going to again give a truth definition, a partial truth definition, and use the same methods. So this gives us some very nice upper and lower bounds on partial consistency statements. So I'm going to switching topics here. As I said at the beginning of the talk, I'm happy to take questions, and this is actually a pause because it's between part 1 and part 2 of the talk. So if anyone wants to jump in with a question here, I'll take it, or otherwise I'll keep going. Okay, so now back to Gödel's 1936 paper on the lengths of proofs. So
sorry, a question from the audience.
Okay, very good.
Yes, I wanted to ask, this could be done with many other complexity measures which are exhaustive. Is this right? So you could argue Gödel's argument for many other complexity measures, insofar as you can find all proofs of lesser complexity. Is this so?
Oh, good point. I had not considered this. Let me think what kind of complexity measures you're thinking of. Anything that bounds the logical complexity of formulas would work. But did you have another complexity measure in mind?
In mind, it will not work. Maybe the number of steps, not.
Oh, it does work for the number of steps, as I just remarked at the bottom of the slide here. But I agree, there's probably more that could be done with this. But I have to say I haven't really considered it. Okay, that's a good comment. I'll have to think about that.
Thank you.
Okay. So now Gödel in his 1936 paper, he worked with step length, not symbol length. And he talked about higher order systems of arithmetic. So this was shortly, like just seemingly appeared just a year or two, or he did the work just a year or two after his famous paper on incompleteness, And he even has a remark at the end of this paper about the robustness of recursive functions, that different theories extending PA, the numer-wise representable functions are all the same class of functions that he apparently didn't notice in his earlier paper, and he remarked that here. So this is the very early days of incompleteness. But he stated the following theorem of let Zi be I plus first order arithmetic, to use his notation. So Z0 is piano arithmetic, C1 is second order of arithmetic, and so forth. Zi plus 1 has super recursive speed up over Zi in terms of proof length. Namely, take theorems phi of Zi, there's no recursive function bounding the step length of the shortest Zi proof of phi in terms of the step length of a Zi plus 1 proof of phi. So of course, Zi plus 1 proofs encompass Zi proofs. So the step length of Zi plus 1 proofs are no worse than the step length of Zi proofs, but they could be substantially shorter. And the way Gödel stated it, there's no recursive function bounding the increase in a curve when going from a proof in Zi plus 1 to a proof in Zi. And actually, even a stronger result is obtainable. I'll show that in just a minute. Gödel never provided a proof of this theorem. The paper was literally, I think, 2 pages long. There was proofs given later by Mostovsky and Ehrenfreund-Mnichilsky for symbol length. And one way to give the proof is you can just go back to the Friedman-Pudlik method of partial consistency statements. Take the phi i's to be the statement con Zi of n. And con Zi of n, of course, has short proofs in Zi plus 1 because I plus first order arithmetic proves the outright consistency of ith order arithmetic. So it certainly has short proofs in the partial consistency statements. But then the Friedman-Pudlik method shows that con Zi of n requires longer and longer proofs in Zi, and you can change this to the t's and get extra long proofs. And then Parikh and Krychek proved the theorem using step length for languages that have unary function symbols, but take plus and times as binary, as ternary relations. Parikh did it for the I equals 0 case, and Krychek generalized it to I greater than 0 case. And then, so this left open how to prove the original theorem of Gödel's, but in fact, we can do this. And let me just slightly strengthen Gödel's statement. Zi plus 1, the theorem here, has unbounded step length proof speed up over Zi. Namely, there's pi 0, 1 formulas phi j, which are provable in Zi. So there's a fixed value k, such that, oh shoot, the subscripts came out wrong. Zi plus 1, the k is supposed to be sitting under the turnstile there. Zi plus 1 has a k-step proof of phi j for every j, but there is no fixed k such that Zi has a k-step proof of phi j for every j. K is supposed to be sitting here. Sorry for the typesetting issue. Okay, so for the proof of this, it doesn't seem to work to use the consistency statements con Zi like we did for the step length, for the symbol length proof. Instead, though, we can work directly with the formulas phi j asserting they need long Zi proofs, right? So it turns out that these formulas phi j asserting they need long Zi proofs, they do need long Zi proofs, but they have constant length Zi plus 1 proofs. And the proof method is pretty much along the lines of the earlier proof I sketched. I'm not going to give it again. A couple things to notice here. We use the Matiasevich's theorem, MDRP theorem about Diophantine equations to get the pi 0, 1 formulas for phi j. Remember, phi j said there does not exist an x such that such and such. So therefore, it's a pi 1 formula, and we can use Diophantine equations. And once we are in the setting of Diophantine equations, we can actually get the constant length proof k, step length, constant step length k proofs in Zi plus 1. So I'm not going to go into more details, but just throw that out as what's going on. So this gives us, again, it's unbounded, not just a recursive. There's just not just that there's no recursive function bounding the speed up, but there's no function at all because we have a fixed length k for the Zi plus 1 proofs of all the phi j's, but no fixed length k for the Zi proofs. Okay. Another good place for questions, actually. Oh, wait, not quite, in a second. Open problem. So let T be one of the standard theories of arithmetic, PA, PRA, etc. What about the giving lower bounds on the step length of T proofs of the consistency of the step length consistency of T up to length n? So in other words, is it, for what functions K do we have that there's no T proof of step length K of n of con sub T step of n? For instance, does it hold with K of n equal n to the epsilon? This seems to be open, right? Maybe there's extremely short proofs in PA in terms of their step length of the step length consistencies statements. And I should say this does have sensitivity to the way you formalize piano arithmetic. So for instance, if Kreisel's conjecture holds, then let's see, well, then we do have short proofs, right? So one way the open problem, one way the open problem can fail to hold with K of n is if all true sentences of the form n plus m equals n plus m and n times m equals n times m are added as axioms, where the underline means the term denoting n's and m's and n plus m's and n times m's. Okay, so just want to mention there is an open problem here, which seems to be of interest, right? Okay, so this was a good place for questions if there were any questions, and otherwise I'll keep going. So, okay, so the third thing was Gödel's 1956 letter to von Neumann. So here's the relevant part of the letter. This was the main bulk of the letter. There was a little bit of stuff which I didn't look up for my talk about greeting von Neumann and so forth. Von Neumann was in the hospital at the time. Don't have to read this slide. It's small font and it's a lot of words. I'm gonna present it again and on 3 future slides where you can actually read it. So don't try to read this one. You'll notice so it starts with one can obviously construct and it ends with simple exhaustive search. So let's go for it. So the first part of the letter says one can obviously easily construct a Turing machine which for every formula F and first order predicate logic and every natural number n allows one to decide as a proof of length n equals the number of symbols. Notice Gödel switched to number of symbols here. Also we have switched to just plain first order logic. We are not working in arithmetic anymore. Let psi of f of n be the number of steps the machine requires for this, and phi of n be the max of psi as a function of n, right? Over strings of, over formulas, right? The question is how fast phi of n grows for an optimal machine. One can show phi of n as greater than or equal to k times n. So I'm going to stop here. I'll come back to the rest of his thing, but here he's just stated a theorem. And so no proof, but I was able to give a proof later on, which I'll briefly describe. So the theorem they just stated is we work with a Hilbert style first order logic. Decision problem of whether a first order formula F has a proof of less than or equal to n symbols cannot be solved by, here's Gödel's assertion, a deterministic k-tape machine in time little o of n. I mean, Gödel didn't mention the k-tape part, but I'm sure he intended it. And so k could be any fixed constant here. So in time little o of n, that would be less than epsilon times n for any fixed epsilon. Gödel used k, but I would have used epsilon, but okay. And then similarly, Gödel didn't do this, but this is the conjecture of Steve Cook. Also cannot be solved by a non-deterministic k-tape Turing machine in time little o of n over log n. So I was able to give a proof of this some years ago. Let me, without going into any details at all, let me just sort of say the ingredients. And if you don't have to read past the first 3 lines of this page, I'll say more than that. But the main point is, the proof is by contradiction. We assume there is such a Turing machine M that decides provability in n steps and little o of n, provability n symbols in little o of n steps. We form a formula F that says, I am not accepted by Turing machine M in less than or equal to delta n steps. Okay. Then we show that if F is true, it has a proof of symbol length less than or equal to n. And we get a contradiction. Okay. Okay. And so the tricky part here is that we need to somehow take a Turing machine that runs in some constant times n steps and transform that to a proof with exactly linearly many symbols that the Turing machine accepts. So the usual thing on a Turing machine running in n steps is there'd be n time steps and n tape positions. And you would write out the whole computation machine saying, the first pass might be, we say, what's the position, what's the contents of the ith tape at time t, right? But of course, there's n many values for I and n many values for t, so that's n squared. Plus, if you're not careful, you have to write out the bits to describe the i's and the t's, and that's log n. So the total length in that straightforward way to write out the formula f saying I'm not accepted in delta n steps would be n squared log n or something like that. So we need something much better. So what we do is we assume, without loss of generality, a machine can be easily modified to have this property that it runs, the tape is partitioned into blocks. Each block has order log n many symbols, alpha log n many symbols. So I think of alpha as a value bigger than 1, right? And we assume the tape heads live within blocks during so-called epochs. So an epoch is a sub-period of the computation, and a tape head starts on a block boundary at the beginning of an epoch, and it moves back and forth between two adjacent blocks. And then at the end of an epoch, it ends up on a block boundary, either the same block boundary it started on or the one to the right or the one to the left, right? And an epoch lasts at least L steps, but it's between L and 4L. It's easy to do that. And then the point here is then, instead of trying to describe the whole Turing machine at every time t, at every tape cell I, we instead describe the state of the Turing machine at the end of every epoch, right? We just give the block contents at the end of every epoch. So we're specifying, every about log n many steps, we give log n many symbols saying what's going on at that point at the end of an epoch. And we represent tape contents with first order terms in the sort of following way. We have, say our tape has symbols 0, 1, and blank. Then we'll have a function f sub 0, function f sub 1, and f sub blank, and a constant symbol c. And a string like 0, 1, blank would be represented by the term f sub 0, f sub 1, f sub blank of c, right? And so then we'll have some relations that apply to these terms that are true if that's what's true at that time and so on. So basically the proof is going to just prove the true assertions about what's true at time t at a given epoch, right? Okay. Well, actually, what we're going to do is for each time t, we're just going to describe the block that's created at time t. We're not going to talk anything about the blocks the rest of the blocks at time t. We're just going to talk about the block created at time t. Okay. So that way we get rid of the square thing, just like that. And then if you think about it, all these facts about the Turing machine computation at the n over L many epoch boundaries can be encoded using these terms, using only order n many symbols to write out all these many facts. Well, why? Because there's n over L many epochs, that's about n over log n, forgetting constants since we're among friends, and we need about log n many symbols to describe the state at the end of each epoch. So it's order n symbols. And then we have to do a little bit extra work to keep track of the topology of the blocks so that when we transition left to right, we pick up the correct block. When we go from one epoch to the next, we have to say, well, what block is to my right? What block is to my left? So we add a little more stuff for that. But that's the idea of the proof. Okay, a little hand wavy, as I said, if you just want to think about the first 3 lines, that's okay too, right? Okay. Complete proof is written out. You're certainly welcome to look at it. So back to Gödel's letter. So here's something rather remarkable. He ends up saying that it's possible that P equals NP without knowing the concepts of P and NP. So, but he goes on, if there really were a machine with phi of n proportional to k times n, or even k times n squared, this would have consequences of the greatest importance, right? Namely, it would obviously mean that in spite of the undecidability of the Entscheidungsproblem, the mental work of a mathematician concerning yes or no questions could be completely, footnote except for the setting up of axioms, replaced by a machine. After all, we would simply have to choose the natural number n so large that when the machine does not deliver a result, it makes no sense to think more about the problem. Now, it seems to me, however, to be completely within the realm of possibility that phi of n grows that slowly. So Gödel's saying here it's completely within the realm of possibility, and his phrase in German was durchaus im Bereich der Möglichkeit liegt, that this NP complete problem is in time order n or order n squared. In which case we have P is equal to NP, because this question of deciding whether something has a proof of length and it's easily shown to be NP complete. And I'm going to come back to this thing about making notes that it would completely replace the mental work of a mathematician by machine. That may be a bit of an overstatement, and I'll argue that in a minute, but it does certainly help considerably, is what I want to argue in a minute. Right, well, let me first finish Gödel's letter. Now, it seems to me, however, to be, oh, you already read this in, just continuing, I repeated this sentence. Now, it seems to me, however, to be completely within the realm of possibility that phi of n grows that slowly, since firstly, it seems that phi of n greater or equal to k times n is the only estimation which can be obtained by a generalization of the proof of the undecidability of the Entscheidungsproblem, which is the proof I just showed you. And after all, phi of n proportional to k times n or k times n squared only means that maybe I should emphasize that word, means the number of steps as proposed to trial and error can be reduced from n to log n or log n squared. However, such strong reductions appear in other finite problems, for instance, in the computation, or for example, in the computation of quadratic residue symbol using repeated application of law of reciprocity. A very nice example, by the way. It would be interesting to know, for instance, the situation concerning the determination of primality of number and how strongly, in general, the number of steps in finite combinatorial problems can be reduced with respect to simple exhaustive search. So, I mean, Gödel has really put his finger here without knowing the concepts of P and NP and without really working at all with polynomial time. I think he's working with linear or quadratic time instead. He's really put his finger on one of the key points of the PNP problem, right? You know, so even before the definitions were here. And I should mention, he wasn't the only one to do this around this time, right? So it's not, he wasn't totally unique, but it was one of the very few people to see this. This seems sort of amazing. He's suggesting that, well, P might be equal to NP. Okay, so I would say, question is, what did Gödel think? Did he believe this was possible? What does durchaus im Bereich der Möglichkeit liegen mean, right? And I would, here's the sort of conventional thing. I'm taking this from earlier paper of mine, but I don't claim any real originality in these thought is, why do we believe that maybe P is not equal to NP? And so a lot of us are mathematicians here. Some of us are philosophers, obviously. So, but let's take a couple premises. So premise one, mathematics, especially the discovery of mathematical truths, is inherently difficult for humans and for Turing machines, even working in concert. And so here, I don't want to say just that you could replace a mathematician with a Turing machine, but I just want to say that it's inherently difficult, even if you'd combine the intuition of a mathematician with the brute force search of a Turing machine, right? And premise number two, this seems completely clear. Some of the inherently difficult aspects of mathematics can be phrased as questions of the form, does phi have a proof of n symbols, where n is not excessively large? So if you accept both these premises, and I guess premise one is the questionable one, right? The conclusion follows that this, the question, does phi have a proof of n symbols, cannot be reliably decided in times kn or k times n squared, with k not excessively large. More generally, to use modern terminology, the question of whether phi has a proof of n symbols cannot be feasibly decided. So if I have a few minutes left, I think, let me come back to what premise one means. What does it mean working in concert? And so let's see what's going on with this conclusion. Suppose that we could feasibly decide the question of whether phi has a proof of n symbols. So let's think about what this would mean. Suppose it's k times n squared with k equals 1, just for the sake of illustration. And you're trying to prove some theorem, like the Riemann hypothesis, I suppose, or something like that, or p versus np. Why not, right? Well, I guess it would have already been decided, right? So we're trying to decide some hard theorem, and you formulate some version of theorem. And here we're talking about arbitrary first-order logic. So you get to choose your language of first-order logic, and you formulate your theorem in first-order logic with maybe with all the useful symbols and axioms you think it needs. You ask, does phi have a proof of, say, 1,000,000 symbols? Okay. Well, 1,000,000 squared is 10 to the 12. Computers are awfully fast now, so probably in about 3 or 4 minutes, get an answer back, right? Doesn't have a proof, right? Well, okay, maybe 1,000,000 symbols not enough. Let's go to 10 million. So, in 4 or 5 hours, you get an answer back, right? So what does this answer back say? Now, here's the nub, right? The rub, I should say. The answer is a yes or no answer, right? No would be informative. It says it doesn't exist, but yes doesn't tell you very much. Now, here one might say, well, what good is that? Yes, there's a proof. We sort of believe it's true, but we don't have the faintest idea what this means, right? So maybe we're not really doing mathematics here, right? But the point is, if you know the answer is yes, you could then start saying, well, okay, maybe how would I prove this in a way that I can understand rather than just take on faith that the answer is yes? So you might say, well, let's try some lemma that would help me prove the theorem. So you'd write out some lemma and you check, does it have a proof of less than n symbols? And maybe you drop your length down to see if it has a short proof, right? And then if the answer is yes, great. Well, you can then work on that lemma or work on lemmas leading to that lemma. So you can sort of binary search your way. If you knew what was true, it'd be a huge advantage in actually proving things, right? Because you would never waste any time proving false things. You could make a conjecture, you could go to type it into the computer, go to lunch and come back, and then you know the answer to yes or no at least, and then you can make another conjecture. So, and even if the answer came back as no, there is no proof, maybe it comes back, there's no proof, and there's also no disproof, right? Well, you could then think, well, maybe I don't have the right concepts. So you can go to a different version of first order logic with new symbols, new functions added, new axioms, and see whether it has a short proof there. Because at any rate, I just want to say that you'd have an enormous advantage, not only in getting yes, no answers out of your Turing machine, but in understanding mathematics. And so one sort of feels like this is too good to be true. So hence P shouldn't be equal to NP. Okay. So who knows? Maybe that's what Gödel had in mind, maybe not, but at any rate. So at any rate, Gödel, however, what my reading of his thing is that he's on the fence. He doesn't have any opinion either way. He's struck by the possibility that something could be true, but he's definitely not convinced that it is true, right? And he's also obviously struck by the fact you can't disprove it. All right, so that is the end of my talk. Thank you very much for listening.